Greetings of the day. I am Dr. Onika Parmar and I welcome you in the course Fundamental of Electronic Engineering. Today we are going to discuss about the small signal model of MOSFET. This is the last session for MOSFET. In this session we will be equipped with the small signal model of a JFET and a metal oxide semiconductor field effect transistor MOSFET. So, in today's lecture, we will discuss about the small signal model, we will give the introduction, followed by the linear amplifier, then we will go for the graphical analysis and load lines, followed by the JFET small signal model and MOSFET small signal model. We will also discuss about small signal parameters, small signal equivalent circuit, problem solving technique for MOSFET AC analysis, small signal equivalent circuit with PMOS. So, let us begin. Field effect transistor amplifiers provide an excellent voltage gain with the added feature of a high input impedance. They are also low power consumption configuration with good frequency range and minimal in size and weight. Whereas a BJT controls a large output current, that is the collector current, by means of a relatively small input current, that is the base current. The FET device controls an output current, that is the drain current, by the means of a small input, and that input is the gate voltage. So, in general, the BJT is a current control device and a FET is a voltage control device. In both the cases, however, note that the output current is a controlled variable. Because of high input characteristics of FETs, the AC equivalent model is somewhat similar than that employed for BJTs, whereas BJT has an amplification factor beta. The FET has a transconductor factor. The FET has a transconductance factor Gm. The FET can be used as a large amplifier or a digital device in logic circuit. In fact, the enhancement mode MOSFET is quite popular in digital circuitry. FET devices are also widely used in high frequency applications and in buffering applications. Buffering means we are interfacing two circuits. So, a buffer is used and FET plays a vital role in those cases. Although the common source configuration is the more popular one, providing an inverted amplified signal, and one also finds common drain, that is the source follower circuit, providing unity gain with no inversion, and common gate configuration provide gain with no inversion. So, there are three configurations. We use common base configuration, that is the source follower. It provides unity gain, and the common source is the most popular amplifier. Also, common gate configuration circuits are used. These provide gains but no inversion. The voltage gain of an field effect amplifier is generally less than that obtained using a BJT amplifier. The FET amplifier provides a much higher input impedance than that of a BJT configuration. The output impedance value are comparable for both BJTs and FETs. So, BJT amplifiers provide high input impedance. Let's move ahead to the linear amplifiers. A linear amplifier magnifies an input signal and produces an output signal whose magnitude is larger and directly proportional to the input signal. The term small signal means that we can linearize the AC equivalent circuits. We will define what is meant by small signal in the case of a MOSFET circuit. The term linear amplifiers means that we can use superposition so that the DC analysis and AC analysis of the circuit can be performed separately, and the total response is the sum of two individual response. So, let us move ahead towards the graphical analysis and load lines. So, figure 1 shows here a NMOS common source circuit with time varying voltage source in series with the DC source. We assume that the time varying input is sinusoidal. So, this is the circuit configuration for a common source circuit with time varying signal source inserted with the gate DC source. So, here we can see a MOSFET. Here it is in common source configuration, that is the source terminal is common for the input case and for the output case. Okay. So, we can find there is a gate terminal that is connected with a DC input and a time varying signal is superimposed on it, that is provided at the input of the gate terminal. Now, as always, the drain current is calculated from the drain terminal, that is ID. RD is the drain resistance and V0 is the point where we take the output, and VDS is the voltage from the drain to source. Figure 2 shows the transistor characteristics for DC load line and Q point, where the DC load line and Q point are functions of gate to source voltage, VDD, RD and the transistor parameters. For the output voltage to be linear of the input voltage, the transistor must be biased in saturation region. So, this figure shows common source transistor characteristics, DC load line and sinusoidal variation in gate to source voltage, drain current and drain to source voltage. Here ID is in the y axis, that is the drain current, and the drain voltage is in the x axis. So, it is represented as VDS, and here we can see there is a Q point which intersects with the characteristics and the load line. The figure shows that the sinusoidal variation in the gate to source voltage, drain current and drain to source voltage as a result of the sinusoidal source Vi. The total gate to source voltage is sum of VGSQ and Vi. As Vi increases, the instantaneous value of VGS increases and the biasing point moves up the load line. A larger value of VGS means a larger drain current and a smaller value of VDS. For a negative Vi, that is the negative portion of the sine wave, the instantaneous value of VGS decreases below the quiescent point or the quiescent value and the bias point move down the load line. A smaller VGS value means a smaller drain current and increased value of VDS. Once the Q point is established, we can develop a mathematical model for the sinusoidal or small signal variation in gate to source voltage, drain to source voltage and drain current. For the field effect transistor FET to operate as a linear amplifier, the transistor must be biased in saturation region and the instantaneous drain current and drain to source voltage must also be confined to the saturation region. When symmetrical sinusoidal signals are applied to the input of an amplifier, symmetrical sinusoidal signals are generated at the output as long as the amplifier operation remains linear. We can use the load line to determine the maximum output symmetrical swing. If the output exceeds this limit, a portion of the output signal will be clipped and the signal distortion will occur. In case of FET amplifiers, the output signal must avoid cutoff, that is ID is equals to 0 and must stay in saturation region, that is VDS must be greater than VDS saturation, that is the drain to source voltage should be greater than the saturation value. So, let us further go towards the junction field effect transistor, that is JFET small signal model. The AC analysis for a JFET configuration requires that a small signal AC model for the JFET to be developed. A major component of the AC model will reflect the fact that an AC voltage applied to the input gate to source terminal will control the level of current from drain to source. A DC gate to source voltage controls the level of DC drain current through a relationship known as Shockley's equation, that is ID is equals to IDSS 1 minus VGS upon VP whole square. So, this is known as Shockley's equation and it gives the relationship between the gate to source voltage controls the level of DC drain current. The change in drain current will result from the change in gate to source voltage. It can be determined using the transconductance factor Gm. It is represented in the following manner. Gm is equals to change in the drain current to the change in gate to source voltage. So, Gm is the rate of change of drain current to the rate of change in gate to source voltage. Figure 3 shows the transfer characteristics. We find that Gm is actually the slope of the characteristics at the point of operation. So, here it shows the transfer characteristics of the transistor. Here drain current is in the y axis and gate voltage is in the x axis. The drain current is represented as ID and the gate voltage is represented as VGS, and the characteristics between these two values, that is VGS and VDS, is shown in blue in color. This is the transfer characteristics and the Q point is represented here. Gm is the slope of this curve at Q point. Here delta ID shows the variation in drain current and delta VGS represents variation in gate to source voltage, and the ratio of delta ID to delta VGS is the transconductance. It is represented as Gm. Now, let us discuss about the small signal model for MOSFET. So, first term is transconductance. The small signal drain current is related to the small signal gate to source voltage by the transconductance. Transconductance is a transfer coefficient relating output current to input voltage and can be thought of a representation of gain of the transistor. This curve shows the drain current versus gate to source voltage characteristic with superimposed sinusoidal signal. Here the slope of the curve shows the transconductance, and in this curve the AC signal is superimposed on the drain current and gate voltage characteristics. VTN here represents the threshold voltage. Transconductance is the relationship between ID and VGS. Gm is equals to delta ID upon delta VGS. Here VGS is equal to VGSQ, that is constant, and it is equals to 2 Kn VGSQ minus VTN. Here Kn is a constant. It is the device parameters. We can also write Gm equals to 2 under root Kn into IDQ. IDQ is the drain current. The transconductance is the slope of the curve. If the time varying signal VGS is significantly small and the transconductance Gm is constant, with the Q point in the saturation region, the transistor operation as a current source that is linearly controlled by gate to source voltage. If the Q point moves into the non-saturation region, the transistor no longer operates as linearly controlled current source. Let's go through a numerical. The numerical is to calculate the transconductance of a n-channel MOSFET. Consider a n-channel MOSFET with parameters Vt n is equals to 0.4 volts, Kn dash is equals to 100 microampere per volt square. The W by L ratio is equals to 25 and the drain current ID is equals to 0.4 milliampere. So, from this numerical we have various parameters, that is we know the threshold voltage, that is equals to 0.4 volts. We know the value of Kn, that is equals to 100 microampere per volt square. We know the W by L ratio, that is 25, and we know the value of ID, that is 0.40 milliampere. So, moving ahead, Kn is equals to Kn dash by 2 into W by L. So, we know the value of Kn, we know the value of W by L. So, if we place them in the equation, we will get Kn is equals to 1.25 milliampere per volt square. Now, assuming the transistor is biased in the saturation region, the transconductance is determined by the equation Gm is equals to 2 under root Kn into I dq. So, we have got the value of Kn, that is 1.25 milliampere per volt square, and we know the value of I dq. I dq is equals to 0.4 milliampere as given in the quotient. So, we place the value for Gm, that is Gm is equals to 2 Kn into I dq. We place the value of 1.25 and 0.4 volts. We multiply them and we get 1.41 milliampere per volt. So, we can get the value of Gm. So, we have calculated the value of transconductance as 1.41 milliampere per volt. Let us note one thing, the value of transconductance can be increased by increasing the transistor W by L ratio and also by increasing the quiescent drain current. So, if we vary the value of W by L, if we change the W by L ratio, the transconductance will change and it will also change with the variation in the quiescent drain current IDQ. The small signal equivalent circuit. The resulting simplified small signal equivalent circuit for the NMOS device is shown in figure 5. This is the small signal equivalent for a NMOS transistor with small signal parameters, and figure B shows the simplified small signal equivalent circuit for a NMOS transistor. So, here we can see there is a NMOS transistor and there is a small signal equivalent of the same transistor. So, capital G, D and S represents the source, drain and gate terminals, G for gate, D for drain and S for source. So, they represents the terminals, and we can see the gate is disconnected from the source and drain. So, we have a VGS value and then there is a current controlled device. So, here we can see the diamond shape is a current source, okay, and it is equals to Gm into VGS and ID represents the drain current. So, small id for a small signal. Wherever we write a small signal model, we use small letters there. Okay. So, ID represents the drain current and VDS represents the drain to source voltage. We assume that the signal frequency is significantly low, so that any capacitance at the gate terminal can be neglected. The input to the gate thus appears as an open circuit or a infinite resistance. This small signal equivalent circuit can be expanded to take into the account the finite output resistance of a MOSFET biased in the saturation region. This effect is a result of non-zero slope in the ID versus VDS curve. Therefore, the drain current equation becomes ID is equals to Kn VGS minus VTN square 1 plus lambda VDS, where lambda is the channel length modulation parameter and is a positive quantity. The small signal output resistance is given as R0, and here is the equation for output resistance. R0 is the output resistance. It is given as variation in ID to variation in VDS, inverse of this. Okay. So, here VGS is constant, VGS is also equals to VGS Q. R0 is given as lambda Kn VGS Q minus VTN square, the reciprocal of this term. It is also equal to the reciprocal of lambda ID Q. This small signal output resistance is a function of the Q point parameters. The expanded small signal equivalent circuit, including the output resistance for NMOS transistor, is shown here. We can see the R0 output resistance goes in parallel to VDS. It is connected between the drain and the source terminal. The problem solving technique for MOS AC analysis, since we are dealing with linear amplifiers, superposition applies, which means that we can perform the DC and AC analysis separately. The analysis of the MOSFET amplifier proceeds as follows. First, analyze the circuit with only the DC source present. This solution is the DC or quiescent solution. The transistor must be biased in the saturation region in order to produce a linear amplifier. Second point is replace each element in the circuit with its small signal model, which means that replacing the transistor by its small signal equivalent circuit. Then analyze the small signal equivalent circuit, setting the DC source component equal to 0 to produce the response of the circuit to the time varying input signals only. The previous discussion was on for a n-channel MOSFET amplifier. Same basic analysis and equivalent circuit also applies to p-channel transistor. Figure 7 shows a circuit containing p-channel MOSFET. So, we are discussing about the small signal for a p-channel MOSFET. Note that the power supply voltage VDD is connected to source now. Also, the change in current direction and the voltage polarity compared to the circuit containing NMOS transistor. The equivalent circuit of the p-channel MOSFET is the same as that of n-channel device, except that all current direction and voltage polarities are reversed. This figure shows the p-channel MOSFET small signal equivalent circuit. Here we can see all the polarities are reversed and we can see the direction for the current in the current source is also changed, and we find that Gm into Vgs is the current source equivalent. So, in this lecture we have discussed about the linear amplifiers, we have done the graphical analysis and the load lines, we have worked on the small signal model for the field effect transistors, we have seen the small signal parameters, we have seen the small signal equivalent circuit, we have discussed about the problem solving technique for AC analysis of the MOSFET, and then we have seen the small signal equivalent circuit with PMOS. So, this ends our lecture for today. In overall, we have completed the lecture for MOSFET in this class. So, we have discussed about the introduction of MOSFET followed by the channel formation. Then we have discussed the VI characteristics of the MOSFET, and then we discussed the small signal equivalent for the device. Thank you for attending the session. Hope to see you in the next lecture.